Here we are. We continue with our series of videos on benzene. In the previous session, we had stopped on the acronym for preparative techniques of benzene. So we explore them in detail. So we start with the D, that is decarboxylation. Number one, decarboxylation. Decarboxylation of benzoic acid or sodium benzoate. Decarboxylation of benzoic acid or sodium benzoate using soda, lime, and heat. Using soda, lime, and heat. So I start with the sodium benzoate. Sodium benzoate is a sodium salt. Is a sodium salt which has this form. So sodium benzoate is a sodium salt of this form. Of that form. You recall we covered this reaction, decarboxylation. Decarboxylation is a reaction where we decarboxylate the reactant. How do we decarboxylate? By removing the carboxyl functional group. So we are going to decarboxylate by removing the carboxyl functional group, and the reagent which is applied in this case is the soda, lime, and heat. Soda lime is a mixture of sodium hydroxide and calcium oxide. So you can as well indicate sodium hydroxide stroke calcium oxide. It as well represents soda lime. So in this case, so within soda lime we have sodium hydroxide. We have our sodium hydroxide. So this is what is going to happen. We are going to remove this group here, because that is decarboxylation. This group here is going to go with that. So that we are left with the two. If they combine, we have two sodium atoms, then followed by a carbon atom and 3 oxygen atoms. 1, 2, 3. Then plus our benzene. Like that. So we have decarboxylated the sodium benzoate to form benzene. Then for benzoic acid, this is what we do. For benzoic acid, we have benzoic acid is an organic acid of this form. Like that. So to decarboxylate it, in step 1, we first react it with the sodium hydroxide. Why do we react it with sodium hydroxide? We react it with sodium hydroxide to form the salt sodium benzoate. So in the first step, it reacts with sodium hydroxide to form sodium benzoate. Then in the second step, we react the product with the soda lime on heating sodium hydroxide. So we react with soda lime on heating. So in this case, in the first step, once it reacts with sodium hydroxide, the reaction of an acid with a base will obtain a salt and an acid. No, the reaction of an acid, the reaction of an acid with a base yields a salt and water. So the salt which will have formed will be sodium benzoate, which undergoes the second reaction. So as a result, among the products we have water. then followed by these other products that are formed when soda lime on heating reacts with the sodium benzoate. So we shall have our sodium carbonate plus our benzene. Like that. Yeah, so that is the first preparative technique. Then our next reaction is from ethane. So here, ethane, to synthesize benzene from ethane, ethane polymerizes, ethane polymerizes in two ways. Polymerizes in two ways to form benzene. So in this case, we have the keyword is polymerization of ethane. So to polymerize ethane, this is a type of addition polymerization. We are going to combine 3 molecules of ethane to yield benzene. So ethane polymerizes in two ways to form benzene, i.e. those two ways, it undergoes polymerization in presence of organo-nickel catalyst. In presence of organo-nickel catalyst. So organo-nickel catalyst, this is an organic derivative of nickel. These are mainly alkyl derivatives of nickel. So in presence of organo-nickel catalyst, at 70 degrees Celsius, or in presence of iron catalyst and catalyst at 300 degrees centigrade. So those are the two ways. The first way, it's when we have organic derivative of nickel at 70 degrees Celsius, and the second way is when we have iron catalyst at 300 degrees Celsius. So the two ways are summarized in these two reactions. So we have ethane. Ethane is an alkyne, the simplest alkyne of that form. So reacting with iron catalyst, 300 degrees Celsius, we obtain benzene. But observe that we have seen that benzene has 6 carbon atoms and 6 hydrogens. So for purposes of balancing, we can have a 3 here. We can have a 3 there. So implying that there are 3 molecules of ethane that undergo polymerization in this case to yield benzene. So alternatively, we can also have 3 molecules of ethane with organo-nickel catalyst at 70 degrees Celsius. Still we obtain the same product. So that is the polymerization of ethane, the second way of preparing benzene. Then we look at the third way, and the third way, that was P from phenol. So from phenol, in vapor phase phenol in vapor phase. Phenol in vapor phase is reduced. Phenol in vapor phase is reduced to benzene by heating it with zinc dust. So we have our phenol. Phenol, by the way, it is also, we shall see that it is a derivative of benzene as well. Phenol in vapor phase with zinc dust heat. So zinc is a metal. One of the key characteristics of highly electropositive metals are strong reducing agents. For example, sodium, potassium, zinc, highly electropositive. It implies that they can easily lose electrons in their outermost shell. So zinc as well is a highly electropositive metal, implying that it is a strong reducing agent. Being a reducing agent, it is going to reduce phenol. Reduction, that is removal of oxygen. It is going to remove oxygen so that we form zinc oxide, then plus benzene. So that is from phenol. So the first three techniques of decarboxylation, polymerization of ethane, and also reduction of phenol, those are the common ways. However, these last two can also be explored. Then the fourth one, the last two, that is from cyclohexane and also from benzene sulfonic acid. The fourth one from cyclohexane here, cyclohexane on heating it with sulfur powder, comma, it is oxidized to form benzene. And sulfur is reduced to hydrogen sulfide. Gas. So this reaction is disadvantageous because the gaseous product obtained in this case, which is hydrogen sulfide, affects the percentage yield of benzene. So we have our cyclohexane. Cyclohexane with sulfur heat. So cyclohexane is oxidized. Oxidation, that is removal of hydrogen. So we remove hydrogen from cyclohexane to obtain benzene. Then the hydrogen that has been removed with sulfur, obtain hydrogen sulfide gas. So that is the fourth preparative technique. For benzene sulfonic acid, allow me abbreviate it as BSA. This is an indirect way. It is not a one-step way of preparing benzene. It is an indirect pathway. So how is it indirect? In this case, BSA is reacted with dilute sodium hydroxide to form a salt. Reaction of an acid with the base to form a salt, and the salt formed in this case is sodium benzene sulfonate. Which is further converted to phenol, How? Further converted to phenol by reacting it with concentrated sodium hydroxide at 360 degrees Celsius and 150 atmospheres, followed by acid hydrolysis. So phenol obtained is oxidized. Phenol obtained is reduced. Sorry, not oxidized. Phenol obtained is reduced. Reduced to benzene. I think these markers are a little bit disturbing me. Phenol is reduced to benzene using zinc dust and heat. So that is the indirect way of preparing it. So this is the reaction scheme. Benzene sulfonic acid is reacted with dilute sodium hydroxide. So this is our benzene sulfonic acid. Reacting it with the dilute sodium hydroxide, reaction of an acid with a base, we form a salt and water. So the salt formed in this case, this salt is sodium benzene sulfonate. Then sodium benzene sulfonate is further converted to phenol. How is it further converted to phenol? We react it with concentrated sodium hydroxide at 360 degrees Celsius and 150 atmospheres. Concentrated sodium hydroxide 360 degrees Celsius, 150 atmospheres. So we require these extreme advanced conditions because the bond between carbon and sulfur is strong. It cannot easily be broken. That's why we require those advanced conditions to form sodium phenoxide, which is further reacted with the dilute hydrochloric acid, or in this case, the sodium phenoxide undergoes acid hydrolysis to form phenol. Then phenol on treatment with zinc dust in presence of heat, we have seen that this yields benzene. So this is indirect way of obtaining phenol, but I put an emphasis on the first three techniques. So I stop there as of now.